My title for my talk tonight is Water in the Dry Land, Adaptation and Mitigation of Prairie Aquatic Ecosystems Under a Changing Climate. So I was asked today about the title, and it's something that I've used a couple of times in some public talks before, and so I sort of forgot where it originally came from. But it was inspired by Trevor Harriot's book, River in a Dry Land. And I just like that imagery of water in Saskatchewan. I think it really conveys what we're dealing with here. I don't study rivers, so I just changed it to water to encompass the research that I am doing. But ultimately, as Britt said, I grew up on Lake Huron. I grew up with a lot of water around me. I spent a lot of time in southern Ontario. I went to Quebec, eastern townships. I did some research out there. My PhD work was actually on the Bay of Fundy. There was a lot of water everywhere I went until I came here. There are certainly questions by my family and some high school friends as to why I would come here if I had such an interest in water. But the answer to that is that it's really important here because we have so little water. The value of it, the necessity to take care of it, to understand it, is just that much more elevated. It's just a little bit more urgent here, and it's something that I think is really, really important to address. It's something that everybody can relate to. I've had so many conversations with people in the public about issues related to water that I just, you don't get in other areas across the country. So, in particular, what I'm going to talk about tonight is water and climate change in the prairies. So, our prairie landscape, as I said, this is a dry land. We're in a semi-arid climate, and we're dominated by agricultural land. We have some native grassland that covers the surface of the province, and we have a very small surface area of water. So what this means is that we don't have very much water, but we have a lot of land, and we have very productive land. We have a lot of nutrients in the soil. We have a lot of additional chemicals that are present naturally in the soil, but also from agricultural practices and other industrial practices. And so when you have a lot of that material over a large swath of land, and then you get a little bit of water, washing that into a small body of water, you get a lot of stuff. And so that lot of stuff creates a lot of potential problems in terms of water quality. So in addition to this, so we already have this naturally occurring situation where we have a dry climate and we don't have much water. So even naturally without us here, the water quality wouldn't be fantastic in Saskatchewan. But now we're confounding this or adding to this these additional stresses of humans coming here and contributing to what's on the land. And then we've got climate change. So our climate projections are suggesting that we might start to see increased frequency and severity of heavy precipitation events, warmer temperatures that can increase evaporation rates. So going forward, it's one thing to deal with what's going on naturally on its own, but going forward, we're going to be faced with some additional issues that I think we can start to, if not get a handle on, we start to understand it so that we can figure out how to adapt and how to mitigate this. So one of the major driving forces of my research is to ask how climate change is going to affect water bodies of the Northern Great Plains. So water issues in Saskatchewan, again, there are a lot of them, and I just have a few examples here to reiterate that we know that water is a problem. Our quantity and quality issues are numerous, and these are just some news articles that I pulled out a year or so ago. And so drought in the south, flooding in the north, we have too much water in some areas, we have not enough water in other areas. This is causing, either way, causing havoc. We have issues with Bill Lake's drainage, which I'm not going to talk about tonight, but again, where the water is not where we want it, and where we're going to put it is an issue that is causing a lot of debate. This is an example from Manitoba, but no shortage of examples in Saskatchewan of algal blooms. So a blue-green algal bloom in Manitoba lakes like Winnipeg. This is a huge problem. Our algal blooms that can be producing toxins can be really damaging to people, their pets, livestock, and so forth. We have boil water advisories, not just in Saskatchewan, obviously, but we do have a lot of these issues in small communities in particular. And so dealing with drinking water quality is a big problem. Oil spills, additional things that we are adding to our water that are contributing to the water quality and issues and concerns that we have about it. One that really struck a chord that has triggered some areas of my research recently as well was the situation in 2017 where more than 200 cattle died on ranch land because they only had salty water to drink. They did not have any fresh water available to them. That water quality was poor for the cattle and they died. And so there's no shortage of issues that we can start to research, but that we need to be aware of, that we need to be concerned about, and that we need to be able to anticipate under a changing climate in order to move forward. So based on this background of not a lot of water, a lot of stuff ending up in the water, I have two major aspects to my research that I'm going to talk about tonight. And so I put them into categories of adaptation to climate change and mitigation of climate change. So the adaptation side is, it's happening, right? We're feeling it already. We know it's going to continue to happen. We are going to experience more extremes in drought, more extremes in floods. We know that the temperature is going to get warmer. What are we going to do about it? How is this climate change going to affect water quality in Saskatchewan? And is there anything that we can do if we can anticipate what's going to happen? Can we manage accordingly? Can we adapt to this? And then the second half of my talk today is going to be the mitigation side of it. And so mitigation is, can we do anything about climate change with our water bodies? So a lot of our research that I'll get into midway through the talk is about greenhouse gases. And that maybe we can use some of these water bodies as carbon sinks or carbon offsets. And potentially there's some interactions in there about how these water bodies could potentially contribute to the mitigation of climate change. So I'll start with the first part about how climate change is going to affect water quality. And again, we've got issues of severe precipitation events, extreme precipitation events, and temperatures that are a part of this. So to get into water quality is, it's not a loaded term, but it means different things to different people depending on what you're using the water for. From my perspective, water quality is primarily for recreational use. And I'll talk about agricultural ponds as well. So in some cases it will be for livestock use, livestock watering as well. So this is not drinking water that I'm going to be talking about. This is more recreation, exposure, and general ecosystem health. So for water quality, what is going to control it? And so if we've got a water body, and I have this example here of this is a dugout, because I'll talk about the agricultural ponds, these man-made ponds, quite a bit throughout my talk. But you've got a body of water here. Is that going to work? Yes. Okay, so a body of water here, and you've got some salts, and then you have nitrogen and phosphorus. You've got a lot of other things that are going to be dissolved in it, some solutes. But these are the things that I'm mostly talking about today. So nitrogen and phosphorus are nutrients. You have more of them. The lake is going to turn green. Where these come from, there are several sources. So you can get nitrogen and phosphorus from the land. So if fertilizer is applied or you have naturally productive soils, you get some precipitation landing on the land. This might end up getting washed into your water and contributing additional nutrients here. Additionally, the precipitation might come and soak into the soil where there's additional nitrogen, phosphorus, and salts in the soil as well, and you can get some flow that's bringing this into the water there. We also have groundwater sources, primarily the salts. So we've got all of these different things that are contributing to the amount or the concentration of the salts that you have in the water and the nitrogen and phosphorus in the water. So contributing to this as well, I have this additional arrow of evapotranspiration concentration. So again, we're in a fairly dry climate, so evaporation can be really high. So we lose just the water, and what's left behind is even a more concentrated solution of these nutrients and these salts. Okay, so there's things loading the material into your water, and then if you get a lot of evaporation in there, then you can also make it more and more concentrated. So the more concentrated it gets, the worse the water quality is. So one potential way that climate change could affect the water quality is that maybe you get precipitation, you get all this extra nitrogen and phosphorus that's been sitting on the land, and it gets washed into the lake or the dugout or whatever. And so if you get a lot of these nutrients in there, then that system might turn really green. You'll get these surface scums potentially. It might start produce, the algae might start to produce some toxins as well, and we can get some water quality issues there. On the flip side, if it gets really dry and you increase this evapotranspiration concentration, so if it gets really, really dry and we really start to increase the concentration of all of the material that's in the water as well, it's going to be green. But in addition, the salts are going to be really high, and this is where your cattle start to die. So there are a lot of different things that we need to be aware of and start to consider. I should add as well, precipitation could come in and dilute. So you could have that flip side of more water actually diluting things and actually making the water quality better. So there's a lot of different factors at play here that we're trying to start to tease apart to figure out what might happen under a changing climate. So I'm going to show a bit of data about the research that we've been doing here. So trying to determine how precipitation and evaporation might impact lake water quality. And this is just a snapshot, very quick indication of what we might expect based on some really fantastic data taken by Peter Levin's lab. And so a student in his lab, Sam Pham, in 2004 went out and sampled 70 lakes across southern Saskatchewan. And then another student, Heather Kay, in 2013 sampled those 70 lakes plus an additional 35 for a total of 105 lakes. And I just have to note that sampling 105 lakes in a single summer is a phenomenal amount of work, and she did an amazing job doing it. That took a lot of time. Anyway, so we've got 2 years of really nice broad distribution, so all those points represent the lakes that were sampled across the province. And again, this one's just a little snapshot here. We do have more analyses that I'm not going to show you tonight. But 2004, the cool thing with these analyses is that 2004 was a really dry year, and 2013 was a really wet year. So we had very strongly contrasting climate in those 2 years that were sampled. So these are just the numbers here, but looking at the nitrogen, the phosphorus, and the salt concentration there. And if we just compare the numbers, the averages among the same lakes that were sampled each time, just the difference, exact same lakes, 9 years apart, wet versus dry, we nearly doubled most of the solutes. And a big one to point out here really is the salinity. So in the wet year, it was down to 1.5. At 1.5, salinity is not totally fresh water, but it's pretty close. But 2.95 is starting to get into, it's about 10% of what the ocean is. So it's not super salty, but this is the average. And you can see the ranges here as well. There are lakes in Saskatchewan that get up to 115 parts per thousand, which is what 3 times what the ocean is. A lot of salt. Anyway, so this is a snapshot, but it just shows you the impact of this wet versus dry year on the exact same systems. This is an amazing amount, like to double the concentrations of your nutrients. That has a profound impact on the water quality and the algae that are going to be growing based on those nutrients. So we wanted to take this a bit further and see if we could get a little bit more predictive about this. Okay, so again, as Britt had mentioned, a lot of the research that I've been doing the last few years has been focusing on farm ponds, on dugouts. Okay? And again, this started working with the Ministry of Agriculture and then also collaborating with the Saskatchewan Cattlemen's Association. And so we're really interested in farm ponds and their water quality and what this means for cattle health. And so delving into this data a little bit more, so the research that I'm going to show you in the next several slides is really looking at which water quality indicators are an issue. So generally speaking, I can say there's a lot of things that are problematic, that the nutrients are really high and so forth, but what do we actually need to worry about? How bad is it across Saskatchewan? What do farmers need to be looking out for? So for the purpose of this talk and some of the research, just some of the specific things that we're looking at. So total dissolved solids, really just salt. Should replace that with salt, but it's how salty it is. Sulfate and nitrate. Sulfate is very toxic to cattle. Nitrate can be at very high levels. And then the third one is the algae, so how green it is. And some of these algae, the blue-green algae that you might have heard about, the cyanobacteria that produce a toxin. It's a liver toxin called microcystin. So I wanted to look at these different components of the water, determine if they were problematic, and then if they were problematic, try to figure out what it is that's controlling them. Can we figure out what we're doing on the land, whether it's just climate entirely, whether there's land use issues and so forth, that will help us figure out what controls these values, and then hopefully that will lead us to some management options. So, in order to do this, we sampled a lot of dugouts as well. So 101 dugouts sampled in 2017. Again, the distribution here across the province, so southern third or so quarter of the province. And then we went back to the same dugouts in 2019, and we managed to get back to 96 of them and sample them again. So what we did was, I say we, my students did all of the driving around and all of the sampling while I got to sit in the air conditioned office. Yeah, so students did a lot of work doing that delivery. So in terms of water quality, we sampled the things that I mentioned on the previous slide. So your salts, your nitrates and sulfates, the algae that's there, the toxins that you're producing. And so then we also want to get a lot of information about the catchments, about the watershed, what's going on there. So what is the land use, what's happening in the soils, what's the content of the soils, what is the permeability of the soils, what's moving through them. The hydrology, I'm not going to get into the details here, but looking at where the water is going, whether it's evaporating, whether it's coming from precipitation, whether it's coming from snow, again, how it's moving through the soil and how it's getting into the dugouts. And then, again, I'm not going to get into the details of it, but we kind of dump it all into a statistical analysis and use that to start to figure out how all of these things on the landscape, again, hydrology, will be impacting the water quality. Can we get these predictive relationships of how this affects your water quality? And then, like I said, try to get towards some management options. Okay, so I have a series of figures that will look like this. And so what this is showing you is the data. So each of these bars represents one site. So there's 100 of them, maybe 96 of them across the bottom. So each bar is 196, and the value that it has for the different water quality parameters. So this is looking at salt. Okay, so what we're showing here is that, and they're just ranked from highest to lowest, just so that you can see the range. Yes.
Which year is that?
This is 2017.
17?
Yeah, 2017. Yeah, so I have some horizontal lines here, and these are, I apologize for the yellow, but these are water quality guidelines for cattle exposure. Okay, so when we look at the salts, what we have here is that the yellow line is poor quality for cattle. So it's not ideal. If any dugout that has salt levels that are higher than this might be problematic for your cattle, but we didn't have any that were above the high or not recommended level. So really what this means is that there was one site out of the 96 that was problematic. All the others were actually under the recommended salt levels for cattle. So even though we do have reasonable salt concentrations, they're not terrible for the cattle specifically in these particular sites. The results of the statistics I've just summarized in the table at the bottom. So solvents here, total dissolved solids. And then based on the analyses, the contributing factors, so those things that came out as significant in our analyses, and then our non-significant factors, the things that we thought might be important, but did not come out as significant. So they're not contributing to the salts. So even though salts aren't a huge problem, we do know that our salts increase when the water permeates better through the soil, this hydraulic conductivity, and perhaps not surprising at all, soil salinity. So if you have saltier soil, you get saltier water. So that makes quite a bit of sense. What we didn't find significant, the depth of the dugout, where it is across the province, it was pretty patchy, but it wasn't any consistent distribution across the province. And also the local evaporation to inflow, so how much evaporation was occurring versus how much water was coming into the dugout itself. So again, by figuring these out, we can say, we really need to be concerned. If you're worried about salinity of your salts in your dugout, then really look at your soil salinity, and you can potentially figure out where to locate it or to dig one. The nitrates. Surprisingly, despite the fact that nutrients, nitrogen and phosphorus are quite high in the prairies, And if we're looking at it from the perspective of cattle health, nitrates were fine. Limits for cattle are really very high. So your recommended nitrate limit for cattle access is 100 milligrams per liter. These values, so this is actually micrograms on this scale, so this is only 3. So we've got one dugout that had 3 milligrams per liter, it's nowhere near 100. So nitrates really weren't a concern for direct cattle consumption. It's going to contribute to the algal growth, but it's not terrible. So again, when we look at the statistics here, our contributing factors, what's interesting here is that deeper dugouts, so new fresh dugouts that are dug 5 meters or so, tend to have lower nitrates. In this case, our hydrology, the evaporation that was happening, was responsible for concentrating the nitrates. And soil salinity again came out. So higher soil salinity probably means there's more nitrogen nitrates in the soil, and that will contribute to it. Non-significant factors, so the hydraulic conductivity, just how the water is moving through the soil, and the land use as well. So whether it's a crop or pasture or wetlands or wet around there. So those are not significant. So one that I found that's really piqued my interest now is sulfate. So when we look at the sulfate in the different sites here, you can see that there were 6 or so that were completely unsuitable for cattle access. So really quite concerning in those sites, like cattle should not be in those dugouts at all. And then we had another 20 or so, that were poor. They were above that yellow line there. So a total of 27% of our dugouts in 2017 had bad enough sulfate that they really shouldn't be used for cattle. And that's a lot, right? It's a quarter. It's a big concern across the province. And the other thing that's really concerning is that when we do the stats, I got a big blank there under contributing factors because nothing came out of our analyses. We don't know what's controlling it. We haven't figured that out yet. We have some ideas of where to go from here. But here we have a situation where sulfates are a problem. We don't know what's controlling it, and therefore it gets really difficult to figure out how to manage for it. So this one, chlorophyll A. Chlorophyll A is essentially how green the water is, the algae that's in there. And I just classified them based on what we do in aquatic ecology. So hyper-eutrophic means that it's a super, super green lake. Okay? It's really green, it's not ideal, you probably don't want to swim in it. And then you can go down, it's a little bit less. There's a lot of algae, that's the takeaway from this. Our lines here we don't have anything above hyper-eutrophic to classify these things. There's a lot of algae. That said, there's not real strong limits. Like algae in itself isn't a problem for cattle. It's whether they're producing the toxins that's the problem. Right? So again, we do have contributing factors. So deeper dugouts are better. They have lower algae. And then again, as the water is filtrating through the soil, we also get lower algae. So despite having a lot of algae in here, what was really interesting as well is that when we looked at the toxins, when we looked at microcystin, they were really low. We only had, I think there were 5 sites where we could even detect the toxin. And just as a side note, the lakes that I had shown you previously that were sampled in 2013, there were way more. I think there were 30, 40 of those 100 sites that had quite a bit of the microcystin. But these dugouts, for some reason, have much, much lower toxins. It's not to say like it might come up, they can be quite sporadic, so there might be periods in the summer where they pop up and we just didn't catch them. But the fact that we had 2 sites that were unsuitable, so it's not like it's never a problem, but it wasn't as big a problem, arguably, as the sulfate. And yeah, actually only 2 that were above the poor level as well. We couldn't do the statistics on this. All of these bottom lines here, like these were all non-detects. So if you've got a whole bunch of zeros, there's not much you can do with the stats because what are you regressing things against? So we couldn't run the stats, so we don't know what's controlling it, but ultimately it wasn't a massive problem across the province. And just to come back, this is just showing you, so 2019 data is on the vertical axis here, and then the 2017 data for the salts, for the algae, and the sulfates. And similar to what we found in the lakes, is that the drier year had higher concentrations of those things. The algae, a little bit more scattered, but ultimately the fact that these data fall below this 1-to-1 line. So if it was exactly the same in 2017 and 2019, they would all fall along this line. But the fact that the salts and the sulfates are lower means that that drier year, the wetter year had less of these water quality issues than the drier. Okay, so what do we learn from this? Again, some of this is not surprising. We do need to be more concerned in drier years. If we have wetter years, we seem to see more of a dilution effect, better water quality. We do also notice that this changes over the season, data that I haven't showed you here, but again, by July and August, when things start to get drier and hotter here typically, your water quality is definitely going to decline. Often we found that deeper dugouts tend to have better water quality. So this wasn't across the board, but typically speaking, we had lower algae, we had lower nutrients if the dugout was deeper. So management-wise, digging like a new dugout that starts at 5 meters is probably going to be better than one that's been around for 50 years and has started to fill in. Management encouraging farmers to dredge their dugouts, which they do occasionally, and there are programs in place across the province to encourage that, is probably going to lead to better water quality. And then coming back to this idea of the sulfate, sulfate's a big concern, and it's something that we really need to pursue in the future to try to figure out what's controlling it, how to measure it, and see if we can get the farmers so that they can measure it themselves, so that they know when to allow their cattle to come into this. Next steps from here, again, this is some more work from Heather Haig, looking at how do we take this information and take it a little bit further and see if we can project into the future based on climate models and what we know about weather situation across the province. And really all this is showing you is that when she mapped out some of the hydrology across the province here, she found that the Northwest had much higher evaporation rates, or a higher evaporation to inflow here than we do down in the southeast. And so it kind of gives us an indication of where we might need to be more concerned about these things. So probably focusing on that Northwest area of the province, in dry years is when we might need to spend a bit more time, a little bit more effort sampling and looking into things. And using some of the work from the exhaustion at Park as well, if we get some good climate projections in here about where things are going into the future, then again, we can start to identify areas of greater concern and potentially develop some more robust adaptation strategies for that. So that was where we are with the water quality side of things, and so I was going to now switch to the mitigation component of it. So the next question is how water bodies in Saskatchewan might affect climate change themselves. So, and it might be a strange question if you don't spend all of your days measuring greenhouse gases in water, but why a water body would be affecting greenhouse gases. But one question that we had several years ago was whether lakes in Saskatchewan were carbon sources or sinks. So the reason we asked this question was that work done in the boreal, lakes in the boreal is where lots of aquatic ecologists want to work. It's nice and pretty and forested and clean lakes where you want to spend your time. Less so here. That research has found that those lakes are actually releasing a lot of CO2 to the atmosphere. So they're producing carbon dioxide. There's bacteria, they're respiring, organic matter and so forth. They release carbon dioxide, you get a lot of it in the water, and it comes out into the atmosphere. Lakes in Saskatchewan, though, and prairie lakes, in the Northern Great Plains really hadn't been studied. And so we wanted to see if these lakes were doing the same thing. So when I first came to Saskatchewan and started working with Peter Levitt, this is one of the studies that we did where we were looking at lakes in the Capel Valley and using long-term data set that Peter has. We were able to look at the greenhouse gases and the carbon CO2, what was happening in these lakes. In addition to this, we had some 70 saline lakes that were sampled. So these were similar lakes that I showed you previously. But just to show you the distribution, so you've got your Capel Valley lakes in red, and then some additional saline lakes that have been studied for several years as well. And so we wanted to look at what that did. And so this is just jumping to the end here, but the Capel Valley Lakes, what was really interesting here that we found is that they are carbon sinks in that they are pulling CO2 into the atmosphere now. But the really cool thing is that they actually shifted over the time period that we looked at. So just this bottom figure here. So this is the carbon dioxide and where it's going. The horizontal line here is equilibrium with the atmosphere. So all this means is that any of the points that are above it mean that there was more CO2 in the water and it was leaving. So it was a source. So they were high, it was higher than the atmosphere. Here we're losing CO2 to the atmosphere and it's a source of contributing more CO2 to the atmosphere. More recently, early 2000s, you see the shift where all the dots end up under the line. And they actually shifted to becoming CO2 sinks. And so this was really interesting. So we got this relationship, it might be a step change, but ultimately it did shift over the time period that we were looking. And so we were asking why this was the case, and I won't get into a lot of detail, but part of this really came down to the pH, how acidic the lake water was, and the fact that it's really changed a lot in that 15-year period that we were studying. So what we're looking at here, so the pH of the system, so 8.5 here. Fresh water is, like pure water is at 7, which would be down below here. We do have very alkaline basic lakes around here. But they started off at about 8.5, and by the end of our record, they averaged about 9.2. So a huge shift in the pH over a 15-year period. And just chemically, that has shifted what's going on with the carbon dioxide. Now it's undersaturated, and we're actually sucking CO2 in from the atmosphere. So we learned from this a lot of things, but that link between pH and CO2 is really strong. And our magic number around here is roughly a pH of about 8.6. So if you have a lake with a pH above 8.6, it's probably going to be pulling CO2 in from the atmosphere, with some exceptions. If it's lower than that, so the boreal lakes that have a pH around 6 or lower, acidic lakes, they're actually going to be releasing CO2 to the atmosphere, and they're going to be sources. So that led us to just scaling it up, how much is being stored. So we did some calculations about this change and what that means for the storage long term, and ultimately the amount of CO2 change, whether it is significant, it really turned out to be reasonably significant. So the total change over the period that we looked at was about 1.7 megatons of carbon. And our Saskatchewan emissions for context is about 7.4 megatons of carbon per year. So it's not an insignificant amount when we add it up across Saskatchewan. And then that there is just showing that there's a lot of additional areas, these semi-areas across the globe that are potentially acting the same way. So this could be globally quite significant. Okay, so what can we do with this? So we've got these carbon sinks, and that's great, but they're natural systems. It's what they do. We have natural sources. It's interesting to look at. But is there anything that we can do to take advantage of this? Can we create additional carbon sinks on the prairies? So this is where the dugouts come in again. These are man-made structures. These are new things that we could potentially add to the landscape. Is there any way that we could potentially build more of them and actually create some carbon sinks here? For farmers, these could potentially be used as carbon offsets. We have that mitigation aspect of it that we could consider. Before we do that, though, we have to prove, one, that the dugouts are carbon sinks, which, 4 years later, we're still working on that answer because that's what we do. So what we really had to do, up to this point, we've only talked about carbon dioxide, but there's more to the story than just carbon dioxide. Okay, so if we're looking at a dugout, we need this full carbon budget. So what this looks like is, yes, we need to know what the carbon dioxide is doing. We want to measure how much is leaving, how much is coming in, how that changes across the season, across the years. And then what happens here is that if the carbon dioxide comes into the water, that can be taken up by algae, and through photosynthesis, the CO2 will be converted into algal biomass, algal material, organic matter in the water. If you get a lot of it and it dies, the sink component here is getting the burial, so that photosynthesis, or the algae dies, it sinks to the bottom. You get it in the bottom of the lake, and at that point, it's a reasonably permanent carbon store. So what we hadn't done up to this point was, we had done a little bit of it, but measuring the sedimentation, so how much carbon is being buried, so what is the actual sink component of this? And then we also have to consider the other major greenhouse gases like methane. So methane is being produced in the sediments, and depending on the conditions in the water column, we might, that methane might start to work its way back out. And methane is a much stronger and more potent greenhouse gas than carbon dioxide, so we need to account for this. And then we also have nitrous oxide. So nitrous oxide is even stronger than methane, and so we need to measure these as well. So the research that we were doing here was measuring all of these fluxes. So the nitrous oxide, the carbon dioxide, and methane, converting them to carbon dioxide equivalents and adding them up. So you get a total amount of how much CO2 equivalent material is coming in or out of the dugout. And then also measuring that sedimentation. So we need, if we're going to have carbon sink, that carbon burial has to exceed the carbon dioxide equivalent flux out of the system. So again, this is the same setup in terms of going into the 100 dugouts, same years that we were out there measuring everything. And so again, my students did a lot of work in order to start to calculate this. So similar graphs as before, in that these are the individual dugouts. Each column here is a dugout, just ranked from low to high in this case. And then what it looks like in terms of the carbon dioxide, the methane, and the nitrous oxide. So in 2017, what we found is that about half of the sites were carbon CO2 sinks. So anything below the 0 means that CO2 is coming into the water. Anything above that horizontal line means it's increasing. So half of them over here, so these half over here, we're sucking in CO2, and then these half over here, we're releasing CO2. And here you'll probably notice that the amount leaving is quite a bit more than what's coming in, and that's part of our calculations. In terms of methane, there are all sources. So methane's being produced here. Every site was, but there's a huge range in how much methane is being produced. But what was surprising is that the nitrous oxide, actually 73% of them were nitrous oxide sinks. And we had expected the opposite. There's so much nitrogen around. We thought that nitrous oxide production would be quite high, but instead we found that they were actually sinks for nitrous oxide, which is promising for these calculations. This work, we also wanted to look at it across the season. So the 2017 data was just done in August. Big blast of stuff that's happening in August. We need to add it up over the entire season because things change, the temperature changes, the community changes. And I won't get into much detail here, but ultimately, this is work by a master's student, Sydney, who is, she's working on looking at the seasonal patterns and seeing if we can extrapolate that so that we can get full yearly values here. So your CO2 sort of declines a little bit higher in spring than it is later in the summer. So this is starting right when the ice comes off and then going nearly to when the ice comes on. So we can start to look at this. So the CO2 has a bit of a seasonal pattern. We do see a peak in methane, so these blips here, so each line represents a different dugout. But June and July is when we see a big peak in methane. And then nitrous oxide, we see a big pulse in spring and then it levels off. So these again, we're adding all this up and trying to figure out our total amount of greenhouse gases that are being produced over the course of the summer, balance it against what's being sedimented. And so the sedimentation side of things, again, trying to measure this is a bit of a challenge, but Ryan Remus, who is here tonight as well, PhD student, has been working on this. And we do have a number, an average carbon burial rate, how much is actually being sequestered in these sites. So if we add it all up, well, I think you'll see the variability is massive in these sites, right? So short answer, the sitting on the fence answer is that some of them are sinks. Some of them are sinks. The ones that are not sinks, it's really because of the methane. So what we've learned from this is that it's the methane that's the problem. It's the methane that if we are going to use these as carbon offsets, we either need to manage the site so that the methane is low, or we just need to be able to design new dugouts that do not have that methane production in there. So if we can control methane production, we do have some potential for these dugouts to become carbon sinks. Yeah, so can we use them as carbon offsets? Like I said, really figuring out whether we can manage them to reduce methane emissions. And data that I'm not showing you here is that, so what is methane related to? Our analyses that we did similar to the water quality, it's actually sulfate is a big thing here. So if we have a lot of sulfate, the methane is low. So we have this problem now, it's not a problem, an interesting situation where if we want to reduce the methane, we could have sites with high sulfate. But then we have high sulfate, which isn't good for the cattle. So I think there's just a way going forward of saying, this is your site. Let's see, if you have the high sulfate, then maybe we start to look at whether we can use it as a carbon offset to keep your cattle out, right? If the sulfate is low, then it's a good source for your cattle. Like, I think it's starting to categorize the sites in that way, and just knowing what they are going to be good for. Yeah, I'm not going to propose adding sulfate, although they do add a lot of copper sulfate to the sites anyway, but that's a different story. Yeah, and so I think there's some options in there that we can start to do. And then there's the scaling up thing. Dugouts are small, they don't take up a lot of the area of the land. You know, is this actually significant enough to make enough of a difference where you could use it as a reasonable or a feasible carbon offset? Ultimately, the answer is that the rates are not huge. The amount, you know, a very rough estimate is that these dugouts are sequestering, the ones that sequester carbon are doing so at a rate that's about double what's being released by the land beside them. So if you scale that up, you need the landscape to have like a third of the landscape to be covered by dugouts in order to offset all the stuff happening on land. So it's not going to scale up super well, but I know, I just started all. Okay, but the good news, additional work done by my student, Sydney, is that wetlands are actually they're behaving very similar to the dugouts. So I think a lot of what we're learning here, we've got a bit of more work to do on this, but I think we can extrapolate these results and these relationships to the wetlands. So this starts to extend things out a lot more, and people have been talking a lot about the value of wetlands, and I'm going to reiterate that here. So if we step back, big picture, the importance of wetlands, I know this is I haven't talked about wetlands up to this point, but they are doing things very similar to what we've learned about the dugouts. And I think encouraging the reintroduction or the restoration of wetlands on the landscape is going to be really important for this issue of the mitigation and the adaptation. So my last couple of slides here are really the big picture of what I've learned in the last several years, working in Saskatchewan on water, and what my recommendations are a really big picture in terms of what we need to do. And so wetland restoration is one that always comes up. You know, I like my dugouts, they're cool, there's a lot you can do on the management side, but the wetlands themselves, you know, do a lot for the landscape. And so if you can get those back, work with Ducks Unlimited, get them on the landscape, you've got not just the greenhouse gas or the carbon sequestration that happens in them, but also the water filtration, the water purification, and cleaning up. I'm not going to talk much about this, but you know, when we're talking about water quality, and when I was talking about things like farmers, you know, needing to know what's in their water and whether it's safe for their cattle, getting more information to the people that are using these sites. It's great for me to be able to go out, or students to go out and collect the samples, but the communication is often limited in terms of how we're getting that information back to the people that are actually trying to use it, right? The farmers, like, should they let their cattle in? And so this is where citizen science comes into play. So where we're starting an initiative, or we're continuing an initiative where we provide some sampling equipment to individuals, to volunteers, so that they can sample water themselves, and they can determine what's in their water and whether it's changing or whether it's safe and so forth. So citizen science, I think, is a big part going forward, giving that agency to people that are on the water and using it directly. And part of that as well is the public education. So we've got a lot of different stakeholders, a lot of people here who are interested, and I don't think we often communicate communicate very well. So farmers are over here, the government's over here, the academics are over here, and we kind of, sometimes get together, but maybe not as much as we need to. And then I always put in this plug on, I always have to put in a picture of me with Justin Trudeau. The importance of water quality testing, I think we have a lot of work to do. The stuff that I've presented today is important in terms of obviously the salts and the nutrients and the sulfates and so forth, but there's so many additional things that we need to be concerned about here. Again, we've got like emerging contaminants, things like pharmaceuticals, heavy metals, microplastics, all of these things that we're making good progress on being able to detect pathogens and so forth, but there's more work to be done there in order to make it more cohesive, more comprehensive, and again, better communications with the different stakeholders. And with that, I've gotten through a lot of material in a long time. So, and thank you so much for the Academics for Climate and the funding that they received to put on this event. There's a microphone in the back. Is there a question?
So Sarah has a microphone, and I have little slips of paper if you want to write down a question.
There's a question in the front. I can repeat it if
there is a potash mine being built by Chrono. Potash requires water. What's going to happen to the water in Regina?
It's a very good question. Yeah, so proposed potash mines and existing potash mines, I do think this is a concern. It does require water quite often, depending on the mine. Some of them are taken from surface water, so they're taking them from our lakes. In other cases, they're proposing to use groundwater for this. When it comes out, that water is not usable anymore, so it cannot be reused. And I think it's very short-sighted to really encourage that the continued expansion of potash mining, because we don't have the water quantity to support that much material. So yeah, it's a huge concern, and I know, Peter, I'm going to point you out as well. He's done a lot of the math and the analyses and looking into this a lot more about the implications and how much water we're talking about here, but it's definitely an issue, and I think it's something that we need to talk about and get into environmental impact assessments more thoroughly.
What can we do to stop it?
What can we do to stop it? This is where we need groups of people to get together and talk to politicians and get some action at the government level. Beyond that, any insights? Peter, do you want to jump in at all or not? What do? We talk to people and we talk to our politicians and we encourage them to get impact assessments going.
Yes, with respect to water, fracking and pumping all that water down and then just to get oil up, to me it seems like a strange way to use water. And I'm also extremely concerned about the permafrost melting, and it releases methane, which is what, 17 times or more powerful than carbon dioxide. One molecule of methane is, I don't know how many times more powerful. But with the permafrost melting around the world, do you really have any hope? I'm sorry, I've served those two.
I haven't, it's a tough one. I haven't lost hope in the sense, I do agree on the fracking side, it's like the potash, very similar. We need to be more vocal about it, we need to keep arguing this. It's not an appropriate way to use our water when we don't have much water and our water quality is already problematic. I completely agree with you there. On the permafrost thaw side of things, yes, that's troubling. What's really interesting is that there has been some more recent research that's actually showing that that's not everywhere. So across the north, there are some different landscapes up there where the permafrost thaw is not releasing methane, and that there are some sinks up there. And so trying to figure out, it's very, it's a huge area, and it is a lot more diverse than we think. And so I think there's a lot of different things going on up there that we don't fully appreciate up to this point. I don't think, it's not a great story by any means, but it's not uniform across the entire Arctic. There are some different things going on up there. Yeah.
Oh,
Yes.
maybe there's hope.
We'll take what we can.
A little bit.
Yeah.
How long do you think it'll take before freshwater becomes luxury in Canada?
I mean, in Canada as a whole, I think we have more time than most. That's not to say that we shouldn't be worried about most other countries as well at the same time. Again, like growing up on Lake Huron, like the Great Lakes, that's a phenomenal resource that we have here, and there are many beyond that there's an amazing amount of fresh water that is in very good shape across Canada. I think in Canada we're fine. In Saskatchewan, I do not have a timeline for this, but I think we need to do what we can now to preserve the quantity and the quality of it as best we can.
It puzzles me why people try to mix climate change and pollution. Pollution is an enormous problem, it seems to me. Whereas climate change, I can only describe it as kind of the hopes of the 21st century. People who show me a person who believes in climate change in Saskatchewan, and I'll show you someone with colossal, incomprehensible ignorance. Now, what we have here, if you study the records of Regina, which goes back to December 1st, 1883, what we have in Regina in southern Saskatchewan is warmer winters, but cooler summers. Now, the idea of cooler summers is totally incompatible with the theory of increased carbon dioxide. Now, carbon dioxide has increased in the last 150 years about 45%, which is gigantic, enormous. So we have this huge increase in carbon dioxide in the last 150 years, and yet we have had virtually no change in climate other than what I've described as warmer winters and cooler summers. And but the real problem here is pollution. I mean, we're destroying the environment. You have no idea, sitting here, what wheat midge has done to southern Saskatchewan.
What has done?
The wheat midge. So what they use for the wheat midge is an insecticide.
Sir, do you want to maybe ask a question to Kerri?
Well, okay, if she wants to ask a question, well, I've asked a question, is to mix the idea of pollution and climate change, and the other is comment on Patrick Moore if he's coming to town. Now, I would suggest that anybody who's interested in this subject should really get on the internet, look at Patrick Moore and all the rest of them, and you'll see that, it's just, okay, let's let Kerri answer.
So I will say on the climate change front, should we get a show of hands in the room of people that believe that climate change is real? I think there are plenty of conversations to be had afterwards about those details. There's also a lot of people in the room. I've not to deflect this, but I know that there are a lot of people in the room that have very strong and have done more research and background on everything that you had talked about the climate change. I will say that the evidence, the scientific evidence, really is not controversial. Climate change is real and it's our fault. And we have a lot of experts in the room that firmly believe and understand that data and are behind that data. And I think I'll leave it at that.
I have a question. On your charts, a very small number of dugouts had very high nutrients of all three. Were those 6 dugouts all the same for the high nutrients in every one, or were they all varied?
That's a really good question. I believe they are all the same, but typically if you get, they do tend to be really highly correlated. If you've got one solute, you've got another. So if you've got a lot of salts, you've got a lot of nutrients. We do see pretty strong correlations between those. So typically, I can't say for sure that those are exactly the same sites, but yes, if it's high in one, it's going to be high in a lot of different ones.
I have a question about lakes. I was interested in the data you presented about the Pell system, where the lakes have flipped from being sources to sinks in the fairly recent past. It made me think about the other lakes we've got in the Saskatchewan River system, in particular, the other impoundments like Lake Diefenbaker. Has any work been done on those as part one? And the second part would be, and what about the projections as the inflow in this entire system shrinks with the loss of the glaciers? And what is that going to do to the possibility of these lakes being better or worse at managing our carbon?
Okay, so yes, Diefenbaker was part of that study, so that was included in it, and pretty much all of the lakes, we had studied additional lakes in there, and they're all very similar, so I didn't get into the data with the 70 saline lakes, but we saw very similar trends with them. They were doing the same thing, seeing the same shift in the pH. My prediction with less water coming through, so if we have less glaciers, water melt coming through, ultimately I think that's going to drive the pH up even further, and so chemically they're probably pulling in more CO2. The problem, the flip side, is that you have less water there, so if you reduce your surface area, if you reduce the volume of the water, then the total ability for it to do that is not going to be as high as it was before. So haven't done the projections there, but chemically it would probably make it a stronger sink, I think. But volume-wise, it might not be.
So the pH going up will compensate for the lack of volume?
Potentially. I'm not sure how it weighs out, but potentially.
Thanks, Kerri. I thought it was interesting, and I hadn't thought about this before until you put it all together, that one of the issues with management of dugouts is that in order to have a really the best situation for your cattle, they suggest dredging, right? But the key to an offset is that burial. And so if we remove that buried carbon and put it in a landfill where it will decompose and then off gas, then those two strategies are completely contrary to each other, such as the sulfate. So you kind of got in that way. I guess I'm just interested in how likely or how much of an appetite you would think there is for categorizing reservoirs for different purposes.
I have no idea. I think that's a great question. Definitely more conversations to be had with the Ministry of Ag. What I will say is that in terms of dredging it out, that is also what Brian is working on for his PhD, is this dry flux. So we're looking at, like, as the dugout dries out, what happens to the stuff on the sides in terms of, does it get respired back out? And yeah, longer term, I think if you have, I don't think it ends up in the landfill. They usually dig it out and just stick it in a pile. So some of it's going to be lost, but usually a pile that lasts quite a while there. So it might still be stored. But these are definitely questions that I think if we were going to use this, we need to know the full, like, 100-year kind of budget.
I was wondering if the data would suggest that deeper dugout would serve as a better sort of storage for CO2.
So the difficulty in us just sorting that out is that it's very difficult to measure the sediment accumulation, the carbon accumulation in it, just because the dugouts are so young, so we don't have a lot of time to collect that data and to figure out how old it is and so forth. So it's sort of confounding in that a deeper dugout is typically a younger dugout, and a shallower dugout is an older one that has more stored. So our data is not answering that question appropriately and sort of confounding that question. So I think I do think a deeper one is better because we do have, the water above it is going to be more stable. You're not going to get resuspension. You're not going to get a lot of stuff happening with that. I think it will be a better, longer store if it is deeper, as I think through that, than a shallow one. But probably. But it's a little tricky based on how we've been sampling.
There's been a lot of questions about water use and especially about water quality. But water monitoring is one that I haven't heard a lot about. Do you know if there is any work going on, especially with, and it kind of relates to water flow from glaciers earlier, with drought monitoring? So how we're using our water versus times of need versus times of surplus. So like dry versus wet years.
Yeah. Short answer is yes, people are doing it. There are, that's a hydrology question, which is definitely not my area of expertise. I know there is a fair bit of monitoring going on in Saskatchewan. Yeah, so I don't have a great answer for you. I'm going to say monitor, but I don't know the answer.
Hi, I have a couple of questions. Should I do one at a time? Okay, so I am interested in the fact that a lot of your research has focused, not all, but a lot of it that you presented here tonight is focused on the influence of the situation on cattle.
Yep.
And to me, I'd be very curious to know about what the changes that we're seeing take place in these water bodies are doing to smaller life forms, amphibians, plants, trees, everything in the whole ecosystem as it's also interconnected. And the question is, and I don't know if this is appropriate, but I'd like to know what the decision was based on to study, to focus on cows. Is it just that you had to choose something, or is there industry funding, or I'm not accusing. Yeah, so that's the first question.
So what I would say for the other organisms, going out and sampling additional, to get the invertebrates, to get the amphibians, it's going to take a lot more time and effort and money in order to do it. What we could do, though, is that it would be very easy to ship those graphs. If we know what the limits are, there should be lots of studies out there in terms of toxicity of these different water quality parameters on different things. We can just move where those horizontal arrows, the lines are quite easily, right? Just move the red and the yellow lines. That would not be difficult to do, as long as those limits are published somewhere out there. And yeah, it was governed by the funding. So the project started on the greenhouse gas side. So got some funding from the Ministry of Agriculture. And so what happened, because it was from agriculture and it was dugouts, obviously we were dealing with farmers. And so I had students out there and I was talking to a lot of different farmers, and that's where their concerns are. And so it's addressing their concerns because that's where the conversation was. And again, then the funding came based on those conversations from the Cattlemen's Association where their priorities lie. So I think there's a lot that we can learn. Yes, it is industry funded, but the chemistry and the biology and everything that we learned from this can definitely be extrapolated to other things, which I think is really beneficial.
Thank you. Can I ask a second question? I'm also very interested in glaciers, and so I'm glad people have been asking. But my question is about the future of lakes in Saskatchewan that are fed by glaciers, and if you happen to know or could point me in the direction of percentage of lakes in Saskatchewan fed by glaciers. I was doing some research for my own work, and I read in the Lake Diefenbaker operations manual that 80% of Lake Diefenbaker's inflow comes from mountain snowfall, rainfall, and glacial wastage. And so I'm deeply concerned about this.
I don't have any better statistics than you. That is my understanding as well. Hell is definitely driven by that. It's coming in. Any of the rivers of south and north Saskatchewan is going to be coming from Alberta, essentially from that glacial melt. And again, we don't have, hydrology in Saskatchewan is really fascinating and frustrating at the same time. I think it's actually David, you that described, the landscape is like just a scrunched up tablecloth, Normally, you'll have these nice landscapes with like sloping sides, and so rain falls here and it ends up in the lake down here. Here, rain falls and you get a lot of it, it might, trickle into something over here, but if it's dry, it kind of seeps, sits, it moves, very scientific. And so it's a big challenge. So I think the smaller ones are definitely, the ponds and the wetlands and so forth are going to be a lot more local. And groundwater as well. So proportion, I think the vast majority of like the good water coming through is going to be glacial origin, and yes, it is concerned.
Thank you.
Just following up on someone's previous question, is the premise of dugouts to increase the cattle population? It seems like the way it's presented, it's about water sources for cattle, as opposed to humans.
Right.
And I'm assuming you're familiar with the Mint declaration from the National Farmers Union. So what I'm asking you is like, are you looking at taking this to the next level, which is to look at the grasslands and the wetlands? Because if we don't stop tillage, it won't matter. You can feed all the cattle you want. The other question is, so I want to know if you're looking at moving to the next step, which is a co-relationship between increasing grasslands, which is useful, and wetlands, and then this whole dugout thing. The second question I wanted to ask is, in relationship to your study, you're looking at CO2 sinks, or the whole question of CO2 and nitrous oxide and ammonia or whatever. Did you look at, if you increase this sequestration of carbon dioxide through dugouts, is that going to be offset by the increase in cattle who are nothing but polluters of greenhouse gas, etc.? So have you looked at the danger of increasing carbon sinks and then carbon credits so that farmers can have more cattle, and those cattle's contribution to the emissions, is that going to offset that carbon, or is it going to make things worse?
So the point of dugouts is not exclusively to increase or support. It's one aspect of it. I think I do agree. I can see the argument that I would much rather have wetlands on the landscape. Absolutely. I think the point of the dugouts is all these wetlands were drained, and now we've got problems of flooding and drought on the landscape, and there's not a great way to deal with it. So what my understanding is that if you dig a dugout in a place where it's more convenient for you to have the water, it's still going to be at the lower point of the landscape. But you can still farm around it and so forth. And so it is a water management strategy. It's not specifically so that you can increase the number of cattle. There's other ways to get water to cattle that aren't dugouts. I don't see the link directly between more dugouts and more cattle, personally. I don't think that that's where this is going. I completely agree that, in an ideal world, and I was going to say everywhere I go, but apparently I didn't say it tonight. I do agree, like wetland restoration, and coming with that is the grassland restoration. I think if we could do anything, getting the grasslands and the wetlands back is the answer. But recognizing what we're doing in the province and that agriculture is happening, how do we deal with what we've got in front of us? I think dugouts are a reasonable potential option. I mean, they're acting like wetlands. I mean, they're not identical, and there can be other things that are not the same. But if you have a dugout, how do we maximize their potential coverage?
Do you see a huge increase in irrigation of crops, and what effect would that have?
I haven't been following that specifically. Not really. There's not a lot of irrigation right now. It's more the dryland farming that's going on. So I'm not sure how the irrigation has changed. I don't have a good answer for you on that one. But yeah, I might have noticed a huge difference in irrigation cycle.
I was wondering if the big dig that happened in Wascana Lake was a contributor to a release of greenhouse gas.
Never looked at that. We have the data. So in terms of pulling out all that stored carbon, then what's happened to it?
Yeah.
That would, I think we'd have to go and, you know, it would be interesting to see if that mound has shrunk, and by how much, and how much carbon that might work out to be versus, you'd have to do some calculations on what's washed out versus what's been respired. It's pretty tricky to figure out, but it's a cool question.
I realized that carbon capture was a fiasco. Could there be such a thing as methane capture? And what would it be used for?
Yeah, I do not know. I'm completely unqualified to answer this question. Just say that loud. Sorry.
Well, if you can capture it, you can burn it
Burn it.
as a fuel.
Yeah. How do you capture it?
How is it difficult?
Are people working on it?
Actually, Joe Gates bought this prototype from northern BC. Two Canadian scientists have built a prototype that takes methane, nitrous oxide, and carbon dioxide out of the air and converts it to a fuel. And that fuel burns without emissions. And you can put it directly into a combustible engine. You don't have to change anything. And they discovered that. They have a working prototype, but Bill Gates bought it. So we're not sure what he's going to do with it.
Good things, I'm sure.
Pardon?
Good things, I'm sure, Bill Gates.
Kerri, I've got, thank you for tonight. Really interesting talk. Just a couple questions that are unrelated. First, I may have missed it with the talk, but why is the pH changing in those lakes? And then the second question, oh, go.
So that was a sticking point. How many years did we try to figure that out? 5 years, we were telling me. So why is the pH changing? It was a really good question. And it turns out what we found is that it's actually the ice cover. So it gets a little complicated, the chemistry, just because it's fairly circular. So the circularity is that if you have more CO2 in the water, your pH goes down. But if your pH goes down, then you get more CO2 in your water. And so it's sort of hard to tease this apart. But what we discovered was that there was also a relationship. So the pH was directly related to the length of ice cover. And so we would get a lower pH with colder winters and longer ice cover. So you get this like cap, essentially. So ice is on the lake and nothing can exchange, right? So there's no mixture of the gases, so it gets capped. So the ice is on the lake and you have all this organic material, really rich, bacteria start to respire and produce a lot of CO2. So if that stays on for a long period of time, you get a lot of CO2 accumulating there and the pH gets lower. And so the pH gets lower and then we have more CO2 and it gets released from the water when the ice comes off. So with the warming, we also have shorter ice cover. So you've got a longer period of time for that CO2 to accumulate. And the pH just didn't get as high. Like so when the ice came off in spring, the pH was a lot higher. So ice would come off and already the pH would be like 8.5 or something. You barely lose any CO2 before it increases and set my heart system again. So it's ice. So it's like a negative feedback.
Thank you. The second question is different question, but it's come up tonight around skepticism and of climate science. And I'm just wondering, can you share with us from your work with different stakeholders, Cattlemen's Association, where you think we're at in Saskatchewan and what do you think we could do to improve literacy of climate science in Saskatchewan?
So my conversations, I think they've been biased in that the way we went about this study was that we put out a call and we said, we're working on this study on greenhouse gases in dugouts. Let us know if we can come sample your dugout. So it was the people that had said yes are the people that are on board. And so the conversations that I've had have been very positive. I really have not had strong skepticism with the farmers that I've talked to. And yeah, the discussions have been, my impression in talking to most people and like going to the municipality of Saskatchewan, anyway, a group of municipalities, and what I found really interesting is that, you know, people are feeling the climate change. Like, people are experiencing it. They're on the land. They see it happening. There was it High River, Alberta, that had that massive flood a couple of years ago? Yeah, that is one community that is not debating any of this. They know it's happening, right? They're on the ground. So you at least have, my experience has been people are feeling it and they believe that climate change is happening. I don't always push to whether it is our fault, right? So that second step of whether it's because of our emissions, I tend to not delve that deeply into these conversations personally, but we just work on that level of accepting that it is changing and what can we do. Yeah, I think maybe not shying away from it would be valuable as a lesson for myself. But it's difficult. It is a challenge and it is a hot topic and people are interested. But I think the interest is good. You know, it keeps people thinking. And I think we just keep discussing it. And having things.
Hi, I just have a comment about cattle, and I'm not a cattle producer, but I've learned a lot about grasslands lately, and grasslands need herbivores such as cattle and bison on them. So let's not totally diss cattle and bison. And grasslands sequester a lot of carbon, they store water, they filter water, and they preserve the soil. So let's try and keep a balanced view about herbivores such as cattle and bison. Thanks.
Really appreciate that comment. Yeah, I think well-managed grasslands, well-managed cattle production has a real strong place in this discussion of being possible.
I actually have a question, recognizing the importance of the grasslands, thank you for your comment, and the importance of trees and planting trees to capture carbon, but we know that trees require a lot of water. Can you comment on that at all?
Yeah, and I think you work with the climate that you're in, so yeah, planting trees in southern Saskatchewan is probably not the most reasonable way to sequester your carbon. Restoring the grasslands makes way more sense. You know, I love those diagrams of the roots of the grasses and the grasslands that are like 10 times deeper than the above-ground biomass there. Yeah, I think planting trees is great in climates where you have the water to grow them. We had also proposed at one point to start to look at, you know, additionally controlling or working with the dugouts to expand it to the riparian stuff. So you will, over time, around dugouts and wetlands, you'll start to get some more shrubby and you know, older trees and stuff. So maybe we can encourage that because it does have the water available for that to grow. And then maybe we can make this whole thing not just the water, but the entire structure and maximize carbon uptake that way. But you know, replacing grass with trees is not going to make a lot of sense.
Well, this has been amazing. Thank you so much, Kerri.